study compactness. The notion of compactness is not so natural as that of connectedness. From the beginning of the topology, it was clear that the closed interval AB of the real line had certain property that was crucial for proving such theorems as the maximum value theorem and uniform continuity theorem. But for a long time, it was not clear how this property should be formulated for an arbitrary topological space. It is used to be thought that the crucial property of closed interval AB was the fact that every infinite subset of a closed interval AB has a limit point, and this property was the one dignified with the name of compactness. Later, mathematicians realized that this formulation does not lie at the heart of the matter, but rather a stronger formulation in terms of open covering of the space is more central. The later formulation is what we call compactness. It is not as natural or intuitive as the former. Some familiarity with it is needed before its usefulness become apparent. So first of all, we will define open covering. A collection A of subsets U alpha of a space, in fact topological space, X is said to cover X if the union of elements of A is equal to X. Here alpha belongs to J and U alpha is a subset of topological space X. So we also call A to be covering of X if X is equal to union of U alpha where alpha belongs to J. It is called an open covering of X if elements are open subsets of X. If elements are not open subsets of X, then we simply call it covering of X. In case of open subsets, we call it open covering of X. Now subcover. A subcollection D of A that also covers X is called a subcover of A. If F is a subset of A is a subcover with finitely many elements, then we call F a finite subcover of A. In other words, this means that there is a finite subset alpha 1, alpha 2, alpha n of J with F equal to U alpha 1, U alpha 2 up to U alpha n, and X is equal to U alpha 1 union U alpha 2 union U alpha 1 alpha n. So this was the definition of open covering and this is the definition of subcover. Now compactness. A space X is said to be compact if every open cover A of X contains a finite subcollection that also covers X. Or a space X is said to be compact if for each open cover A which is equal to union of U alpha where alpha belongs to J of topological space X, there exists a finite subcollection U alpha 1, U alpha 2 up to U alpha 1 n that also covers X. Here notice that the word finite in finite subcover, here we have mentioned finite subcover. The word finite in this finite subcover refers to the collection of F being finite, not that its elements are finite. On the other hand, the word open in open cover refers to the elements in A being open, not that A itself is open in some topology. Means U alpha is open, not that A is open. Now we have some example. The real line R is not compact because the covering of R by open interval A equal to n to n plus 2 where n belongs to Z. Z means set of integers contains no finite subcollection that covers R. Now one more example, the subspace X, uh, which is equal to union of singleton set 0 and 1 upon n, where n belongs to z plus z, which means set of positive integers of R is compact. This is compact. Here this is not compact. Because given an open covering A of X, there is an element U of A containing 0. The set U contains all but finitely many elements, finitely many of the points 1 upon n. Since U is open in the subspace topology, there is n belonging to capital N such that 1 upon n belongs to U for all n greater than 1 upon n. If we select a point of X which is not in U, an element of A containing it, the collection consisting of these elements of A along with the elements of U is a finite subcollection of A that covers X. Means for each n which lies between 1 and capital N, if we select Un which belongs to A with 1 upon n belongs to Un, then F equal to U, U1, Un, and this is a finite subcover of A. One more example, any topological space X containing only finitely many points is necessarily compact because there are only finitely many different open subsets U of X. So in this case, every open covering of X is finite. One more example, the interval which is semi-open, or we also call it semi-closed, it is open at 0 and closed at 1, is not compact. The open covering A equal to 1 upon n to 1, it is open at 1 upon n and closed at 1, and here n belongs to set of positive integers, contains no finite subcovering 0, 1. Nor is the interval open interval 0, 1 compact. This is also not compact due to same argument. On the other hand, the closed interval 0, 1 is compact. The real line R in the trivial topology is compact since the only open interval, open cover are the collection of R and phi R which are finite. So these are some of the examples of the space which are compact and which are not compact. If A is a subspace of X, a collection D of subsets of X covers A. The union of elements of D contains A. In general, it takes some effort to decide whether a given space is compact or not. First, we shall prove some general theorems that show that how to construct a new compact spaces out of existing ones. Then we shall show certain specific spaces are compact. These spaces include all the closed intervals of the real line and all the closed and bounded subset of Rn. Let us first prove some facts about a collection of A of subsets of X is said to cover Y if union of its elements contains Y. So we will prove one lemma. If Y is a subspace of X, then Y is compact if and only if every covering of Y by sets open in X contains a finite subcollection covering Y. Suppose that Y is compact and A is equal to A alpha, where alpha belongs to J, is a covering of Y by sets open in X. Then the collection A alpha intersection Y, where alpha belongs to J, is a covering of Y Y by sets open in Y. Hence, a finite subcollection A alpha 1 intersection Y, A alpha 2 intersection Y up to A alpha n intersection Y covers Y. It means A alpha 1, A alpha 2 up to A alpha 1 is a subcollection of A that covers Y. It means if Y is compact, then every open covering of Y by sets open in X contains a finite subcollection covering Y. Now converse, suppose that the given condition holds. Now we want to prove that Y is compact. Suppose A is equal to A alpha be a covering of Y by sets open in Y. For each alpha, suppose we select a set A alpha open in X such that A alpha is equal to A alpha intersection Y. Then the collection A equal to A alpha is a covering of Y by sets open in X. By the hypothesis, some finite subcollection A alpha 1, A alpha 2, A alpha n covers Y. It means A alpha 1, A alpha n is a subcollection of A that covers Y. It means Y is compact. Now we shall prove one theorem which states that every closed subspace of a compact space is compact. Let Y be a closed subspace of the compact space X. Given a covering A of Y by sets open in X, let us form an open covering B of X by adjoining to A the single open set X minus Y, means complement of, that is, let D is equal to U alpha, where alpha belongs to J, be any covering of A by open subsets in X. The complement X minus A is also open in X. It means B is equal to A union X minus Y. Some finite subcollection F of B covers X. If this subcollection contains the set X minus Y and we discard X minus Y, otherwise leave the subcollection alone. So it means F is equal to U alpha 1, U alpha 2 up to U alpha 1 and X minus Y for some finite set of indices alpha 1, alpha 2, alpha n belongs to J. The resulting collection is a finite subcollection of A that covers Y. That is, G is equal to U alpha 1, U alpha 2, U alpha n is a finite subcollection of D and it covers Y. It is alpha n. Hence A is compact. Now one more theorem. Every compact subspace of a Hausdorff space is closed. Let Y be compact subspace of a Hausdorff space X. Now we shall prove that X minus Y is open so that Y is closed. Suppose X naught is any point of the set X minus Y. We show that there is a neighborhood of X naught that is disjoint from Y. That is, we prove that X naught does not belong to Y bar, so that Y equal to Y bar is closed. Y bar means closure of Y. For each point Y of Y, let us choose disjoint neighborhood Uy and Vy of the points X naught and Y respectively using the Hausdorff condition. So Uy intersection Vy is equal to empty, means they are disjoint. The collection Vy such that Y belong to Y is a covering of Y by sets open in X, since Y is a subset of union of Vy's where Y belongs to Y. Therefore, by compactness of Y, there is a finite subcollection Vy1, Vy2, Vyn that also covers Y. It means the open set V which is Vy1 union Vy2 union Vyn contains Y, and it is disjoint from open set U equal to Uy1 intersection Uy2 intersection Uyn, formed by taking the intersection of the corresponding neighborhoods of x2, x0. For if z is a point of V, then z belongs to Vyi for some I. Hence, z does not belong to Vyi, and so z does not belong to U. It means U is a neighborhood of x0 disjoint from Y, as we wanted to prove. Now we have one more lemma. If Y is a compact subspace of the Hausdorff space X and x0 is not in Y, then there exists disjoint open sets Y, as open sets U and V of X containing x0 and Y respectively. So here I want to give one example. Once we prove that the interval means closed interval AB in R is compact, it means that any closed subspace of AB is compact. On the other hand, the interval which is semi-closed or open interval AB in R cannot be compact because they are closed in the Hausdorff space, because they are not closed in the Hausdorff space R. One needs the Hausdorff condition in the hypothesis of the theorem. Consider, for example, the finite complement topology on the real line. The only proper subsets of R that are closed in this topology are finite sets. But every subset of R is compact in this topology. Now one more theorem. The image of compact space under a continuous map is compact. Suppose F is a continuous map from a topological space X to Y, and let X be compact. Now we want to show that Fx, which is the image of X under F, is also compact subspace of Y. Suppose A is equal to collection of U alpha, where alpha belongs to J, is a covering of Fx by open subsets of Y. It means F inverse U alpha, where alpha belongs to J, is an open cover of X. It means by compactness, there exists a finite subcover F inverse U alpha 1, F inverse U alpha 2, F inverse U alpha n, because these are open in X because F is continuous. These are all open. It means the set F equal to U alpha 1, U alpha n covers Fx. It means Fx is a compact subspace of Y. One important use of this theorem is as to verify that a map, there is a map is a homomorphism. Suppose F is a mapping from X to Y be bijective continuous function. Bijective means 1, 1 and on 2. If X is compact and Y is Hausdorff, then F is a homomorphism. So we shall prove that images of closed sets of X under F are closed in Y. This will prove that continuity of continuity of F inverse. If A is closed in X, then A is compact. Therefore, F is compact by this theorem. Image of compact space under a continuous map is compact. Since Y is Hausdorff, therefore F is closed in Y. So we have utilized the theorem as a tool for verifying that a map is a homomorphism. Thank you.